Okay, so what questions do you have? Not everybody wants. What was your favorite thing about the tour?
The dog.
The dog? That's funny. Yeah. It was a cute dog, yeah. What? Yeah, the evidence room. It was so much better. I took a picture on the wall. If you follow me on Facebook, I put a picture on Facebook of what the old evidence room used to look like. That was on the wall as we were leaving one of the places. You know, had pictures everywhere, and I saw it. And I pulled my camera out and took a picture because that's the only connection I would have to the old place is to have that picture. And you can see the guns are just stacked up against the wall, and the evidence is crammed on the shelves and everything like that. I'm sure it was organized, but it looked like my closet at home. It was awesome. And so the new place obviously is so much better. They had those rolling cabinets. That was pretty cool. Talking about efficient storage. I mean, you really only need to walk between two of them, so you can cram them all together and just roll it over. I was looking at the track system and how easily it moved because she was just pushing it along. She was pushing 2 or 3 of them at one time. That was cool. Yeah. In the narcotics room, that was, yeah, it did, didn't it? Yeah. It's a lot of that plant-like matter. Green plant-like matter. That's one of the 5 Ps, right? Plant-like matter. Yeah. It's in there. It's stinking the place up.
Also, did you notice they had 2 people when they cut out and pasted onto that when they were moving the evidence?
Yes.
2 of them that they had cut out. So it was just there was one on the side, but one in the middle too. That was.
Yeah, and they may have already been like at the other site, I don't know, but yeah, they were part of the team. So I thought that was nice. Yeah. Cool. The building seemed bigger on the inside than the outside. I was like some kind of Harry Potter mojo going on here. But it was the second floor was wider than the top floor. Yeah. But it's kind of crazy. All right.
Homework 12.
Yes?
Question 13, which is the CIE.
Yes.
Could you just go through that one?
Sure. Yeah.
Do you have to calculate that one by hand?
You can probably estimate it, but
Because I was trying to work it out, and I had not the right answer working it out, like through Excel, but I was wondering if, it's going to be a question on the exam day, I can do it by hand, and that part, I got confused when I was converting it from standard RGB values to 8-bit RGB, key values, with the equation
yes.
for correction. That's what I was confused.
Yeah. So let's see if we can eliminate them. So at least we can eliminate it and see. So let's look at the answers on this one. So just for those that are at home, we're on let's see, quiz 12. Number 13. So it's a 0.7, 0.64, 0.09. And so this is the CIE values, and we want to know what the 8-bit standard RGB values are. Okay, so if we're looking at these range from, each one of these should range from 0 to 1. I'll call it X. I'll just put an X there. I've got that backwards. Put 0 on this end and 1 on this end. It's less than 1 and greater than 0. Okay, right. So it's and then they might, if you do the analysis, they might come in at like 1.1 or something. It could be a little bit higher, but we cap them at 1. So between 0 and 1. And so if it's 1, this would correspond to a 255, and the 0 would correspond to a 0. So it's going to be some range when we get to the 8-bit RGB values from 0 to 255. Now, it's not a straight linear conversion because we have that 3 by 3 matrix. So if we were to calculate this, we would do the ICC matrix to convert it over to sRGB values and then multiply that by 255. Okay, so you can't just take 0.7 and multiply it by 255. Okay, we'll do the actual calculation, but we do know that if it's something that's really close to 0, like the 0.9, then it's not going to be a 255. Okay, so answer D is out. So if you look at answer D, you see that 255 in the third slot? We know that's not the right answer because this is roughly R, G, and B. And this is saying B is really low. So you can look at any of those that have a really high B value, and you know that's not right. Okay. What about answer B? What's wrong with it? 315. Yeah, those are capped at 255, and so answer B is out. Okay. We know that R and G are pretty large. We've got a 0.7 and a 0.6, and so we really couldn't tell the difference between A and C. Maybe they both, when you multiply by that 3 by 3 matrix, are greater than 1, and so then they're capped at 255. So C is a possible answer, but we see that this G value is less than the R value, and so that's compatible with answer A. So if I'm looking at this and I'm on a test and I'm like, I don't have enough time to do a 3 by 3, that's 9 multiplications and 3 additions, then I would guess A. Does that make sense? Okay, how we walk through that? Okay, but let's go ahead and, just because this is homework and I want to reinforce it, one more time, let's go find that 3 by 3 matrix. Okay, so I'll start writing out the problem if you'll find the matrix for me. So somebody has their notes on the thing. 0.7, 0.64, 0.09. And that's going to be multiplied by this 3 by 3 matrix.
I have it right.
Okay. And so this is going to give us, let's see, top row times first column is the top value, top row, second column is, yeah, okay. So it'll still be a horizontal. Okay, so go ahead and write them, and you can go just truncate them to 2 significant figures. Okay. 3.2. Go into the next column.
Negative 1.5.
Okay.
Negative 0.5.
Okay.
And then negative 1.0. 1.8. Or 1.9. Sorry.
Okay.
0.0. 0.1. Negative 0.2. And then 1.1.
Okay. All right. Now, what we do with matrix multiplication is, let me change pen color here. This top row is going to multiply by this first column and give us this first cell value. Okay. And so you take the 0.7 times the 3.2. Let me just say, let's write 3.2. Let me say 0.7 times 3.2, and then 0.64 times the minus 1 is equal to negative 0.64, and then a 0.09 times 0.1, so 0.009. Okay, so the 3.2 times 0.7, someone do that for me. So that's 21, 22.4. Yeah, so what is it? 2.24. 2.24. Okay, so then we add these up. And so this 0.64 is negative, so that's going to bring that down a little bit. So if you'll add that number, those 3 numbers for me.
1.6.
Okay, so we'll say 1.6. So this first number is 1.6. Okay. Does everybody see how that's done? Okay. Then we have those same 3 numbers, this top row of our matrix over here, which there's only 1 row, but that row times the second column gives us the second column number over here. Okay. So 0.7 times the negative 1.5, 0.64 times this, and the 0.09 times this. So negative 0.7, negative, so 1.05, negative 1.05, is that right? Calculators would be helpful. I did that in my head. Is that good? Okay. And then this one, it's roughly 2, so 0.64 times 2 would be 1.2, so that's a positive. And then this would be a 0.018. Is that right, or 0.0018? 0.018. Okay, then we add all those up. Zero 0.13? Okay, thank you. So after going through this matrix, we see this is quite a bit lower than the R values or the X values. So that's, and then the last one, and then so cut the 0.7 in half and change the sign, so that's 0.35, negative 0.35. Is that correct? Yeah. So essentially 0.25, negative 0.25, it looks like. We add back in 0.1. What did y'all get? What's that? Yeah. Okay, so that's our 3 values. Then we multiply each of these by 255. And if it's greater than 1, we cap it at 255. So this first one's capped at 255. Then 0.13 times 255 is? Okay, 133. 133, okay. Oh, 33. Whew, that's what I was worried about. I was like, hopefully this works out. We're a little bit off of that, 133. And then this one is less than 0, so we're going to cap that at 0. So we're off from the answer A, but it's certainly not C. So I don't know where, I mean, I have to go back and see if, why it's 135, but that's the procedure that I was looking for you to reinforce. Okay. We've covered matrix multiplication in PChem 1 a couple of times. Apparently, let's see, do y'all take integrated? Y'all do integrated? Okay. It's in there, and it's here again, revisited. So just trying to reinforce that skill as you go through school in chemistry. You don't come across linear algebra much, but it's helpful to know the basics of matrix operations, things like how we do matrix multiplication. Okay.
I'm guessing it's because there's not enough precision in the matrix.
It could be, yeah, because I mean, maybe some of those things would change, but it seems it's odd that it's often the first, most significant digit, right, versus the least significant digit.
Yeah,
So
I remember doing it with the matrix multiplication. It came out.
it did come out. Okay, all right. So yeah, something's we're missing a little bit. Yeah. Okay. What other questions? I know that was long and probably more than you wanted, but it's good review. Yeah.
So then we don't really necessarily have to convert everything by hand or show work. Like, so if I Because I was trying to do it
Like if you did this and I was looking at it and you bubbled the wrong one or whatever, but I was looking, I saw your work, I'd give you like 3 out of the 4 points or something, you know.
Okay. 'Cause,
Yeah.
I was just really worried about. I guess my part is converting from the standard to the 8-bit. Like that
Yeah.
portion, like by hand, just gets me somewhere. But you just really just multiply by the 255.
Yeah. Yeah, I capped it at 0 and 1 and multiplied it to 255.
Okay.
Yeah.
When it comes to the structures that we need to know,
Yes.
is that including the biopolymers and natural fibers, or is it more focused on the polymers and synthetic fibers? Because the last two.
Yeah.
It's a parts on the polymers and synthetic fibers that says like know these structures.
Yeah, that's right.
But I didn't see that on the previous.
On the biopolymers. For the biopolymers, I guess off the top of my head would be you should be able to recognize when it's amino acids joined together versus carbohydrates. Like if you see all those sugars with the OHs, you know that's a carbohydrate. Okay. If you see the amide linkage, right, where the NH and the C double bonded O, those are amides, amino acid type linkages, and the different R groups or whatever. That's a protein, or a biopolymer that's a protein. And then if you see, we haven't really looked at the structures of DNA, so I probably won't put that on there. But you should be able to. Those are the 3 main biopolymers. Is there's DNA, there's protein, and there's carbohydrates. Yeah.
Could you
Yes.
explain the long pass filters?
Yeah.
It looks like a blue color. I was so confused.
Okay, for sure. Yeah. So let's look at that. Yeah. So we have a couple of filter problems on here. Okay, so let's look at number 5 on the last quiz. And I went ahead and kept the one from the notes just because it has so much helpful information on it. So we're looking at this filter, and this is transmittance. On the y-axis, wavelength on the x-axis. We have 700 over here. 400 over here. Okay, so that's the visible region. And so if something is up here around 1, or I'll say 100% or 1, right? If it says 1, we know we're just showing transmittance. That's I over I naught. If we've taken that times 100%, then it's percent transmittance. But still, the top is 100% of the light's going through. So if you see a curve that's going along like that, this light's being transmitted since it's at the top, and then it'll drop off, and this one drops off at around 500, so it drops off like that. And so we have this edge wavelength of 500. And so this is the thing that you should memorize, and that is the colors. If you remember Roy G. Biv, right? So R is over here on the right, then orange, then yellow, then green is right here around the 500 region. And then this is blue, indigo, and violet. Okay. But all of this is blue down here. There's just a bit of green right around 500. And then you get to 550, it's yellow, 600's orange, and 700's red. And so this is cutting out. See, this is the light that doesn't get through. And so looking at those choices as to what color this could be, it's cutting out some of the green, it's cutting out all the yellow and the orange. The only thing left are the blues and the violets. Yeah, so this is going to be a blue filter when you look through it, because the transmitted light is blue. And if you were to flip this filter, so if it's coming along here and it's got like a 500 nanometer edge, and it's transmitting all of the long wavelengths, this is going to be, how would we describe this filter? What kind of pass would it be? Long pass. I kind of hinted at it. And there's another way to write that too. So long pass, what's equivalent to a long pass? If we're talking about energy, low energy. So it's a low pass filter too. So low pass filter, long pass filter, those are the same thing. And then this is passing the yellow, the orange, and the red. And so if it's passing all three of those, then it's the yellow. That's what your eye would respond to and interpret as the color. So even though the red light is hitting your eye, the yellow light's hitting your eye too. And so it's sort of the short wavelengths give priority. You would see that as yellow. Because you're getting a little bit of that green, a little bit of the red, and so that would show up as yellow. You know, on the computer, you've got RGB. If you go in and you type in 100% red and 100% green and 0% blue, the color's yellow. So you're getting all of the green, all of the red, or a lot of the green and the red, and that's a yellow color to your eye. Okay. If it was maybe moved over to 600, so then we've got a filter that looks like this, and it's an edge wavelength of 600. Then we're getting the orange and the red, and so it would look like orange, okay? Because it's cutting out the yellow, the green, the blue. It's cutting those out. And so again, if you've got orange and red, it would be orange. And then if it's cutting, you know, past 600, it would be red. So which of these would we combine in a fluorescence situation? So we have our evidence here, and we've got our crime light. Let's say we have a xenon light, white light. Okay. Filter. That looks ugly. Got to slow down. Okay, and then we have our camera over here. Right? And then we've got a detection filter. And I'm going to call these filters 1, 2, and 3. Which one would you put in what slot? To get good contrast in your image. Specifically, you may want to look for fluorescing compounds. And so which one do you want to cause the fluorescence, and which one do you want to detect the fluorescence? Yeah, so you want one filter for excitation and one filter for detection. Which of those three filters do you want to use?
You would want the short pass for the excitation.
Okay, so we didn't label this one, so that's a good point. So what this has also two ways to label it. Let's do both passes here. And so you said short pass. Is that what you're, yeah, is this the short pass? Because it's passing short wavelengths. What's the other? High pass, yes. So high energy passing or short wavelength passing, those are the same thing. So you said you would put that in the slot here. So we put the short pass in slot 1. That's correct. That's the right answer. Okay. So it's letting blue light hit our sample. What filter do you want in the detection slot? One of the long pass. They're both, actually both of these are long pass. So this is really, you probably try both of them, honestly. Because the fluorescence is going to come at longer wavelengths, right? Remember the Jablonski diagram? We have excitation, then we have the little pachinko game where the vibrational redistribution of energy, and then it gets to the bottom of an excitation spot, and then it fluoresces down. Well, because of that relaxation, that means that the energy of the fluorescence is lower than the excitation energy. What's lower energy is longer wavelengths. So all of the fluorescence is always longer wavelength than the excitation. So you want always a short pass or a high pass filter for your excitation, and then a long pass or a low pass filter for your detection, always. Because that's the way the pachinko game is played. We send the molecules up, they relax a little, and then they give off lower energy, longer wavelength fluorescence, if they fluoresce at all. But if they fluoresce, it'll be a longer wavelength. So then I'm going to change my pen just to emphasize things here. Let's go with the yellow. And the reason I would say that, let's try that first, because that's going to be more light because we have a bigger window here. So we're going to let more light through so we have better signal, okay? Maybe that won't give as good a contrast as the orange filter. So we would try both and see, okay, well, the orange is really showing better contrast, and so we'll go with that. But you would try both, and so then slot number 2 or 3, filter number 2 or 3 would go in the detection slot. Okay. I've asked that. That I'm not saying that will be the written question, but that has been the written question in the past. It's like you've got a filter kit, you've got a camera, you've got a light. What do you put in front of the light? What do you put in front of the camera? You know, and so that's totally legit. This idea of using filters to enhance contrast and you describe, you know, what you did and why you did it and what are the advantages and disadvantages. What if I wanted to use an LED? Do I need a filter? Like if I got a crime light, what wavelength of crime light would I want to use? Your choice, right? If you had the catalogs, I'm going to go buy a crime light, right? And get rid of this heavy xenon lamp. So I'm replacing what piece with my crime light? Obviously this piece, right? Here's the white light and the excitation filter. So I can take all of this here and I can get rid of it and substitute it with an LED flashlight, one of these fancy crime lights. It's like a high-powered flashlight.
So would you use the blue crime light? Because you didn't do-
Yeah, so I was using a blue filter setup on my white light, so why don't I buy a blue crime light? Now they make violet crime lights. Again, you may want to buy an assortment, but if you're going for fluorescence, higher energy is better. Okay, so you may want to go with the more closer to 400, or maybe even 385. They make some 385s that are they're in UV, they're near UV, but so you probably want the shortest wavelength you could get. The trade-off is that that's not as bright typically. It's not giving as many photons, and maybe technology's caught up with it. But in the past, the UV lights did not give you as many photons as a visible light. Just the difficulty of making UV emitting LEDs, right? But they may have gotten better. Okay, so but if you have a 235 or a 335 or 319, one of these really deep in the 300s, that's a UV fluorescent light. I mean, it's great, and you put that on the keyboard and junk just glows like crazy. And really, you then can use almost the whole visible spectrum for detection because it's in the UV, and your eye's not even sensitive in the UV. So everything you see is fluorescent. You might wear plastic glasses just to protect your eye from scattered UV. And so you put on your plastic glasses that are clear, shine that UV light on the table or evidence or bed sheets or curtains, and you'll see biological stuff everywhere. Don't do it. Don't go to a hotel and do that. Okay. I'm sorry, that was bad.
So I have a question regarding the biopolymers again.
Mm-hmm.
So on one of the slides it said to know all these, and it was one of the tables there was the change with polymers. So do we need to know?
That was not the biopolymers. That was the
It was the
synthetic fibers. Yeah. Okay.
So what exactly do we need to really take away from that? Is it like the name? The name?
Yeah, if you see the monomer, like if you see the Teflon monomer, okay, that's polytetrafluoroethylene, And if you see the styrene monomer, okay, that's polystyrene, you know. So just recognizing those. You have to make some flashcards, you know, and just hack your way through those. The only ones that are kind of tough are the methyl methacrylate ones and polyvinyl acetate, because they look so similar. Yeah, it's just the direction of that acid group in the middle. The ester, there's an acid in the middle. And so one way it's facing away from the polymer and the other way it's facing towards. That's the way I can keep those. The acetate it's like it's been acetylated. So that last little piece is an acetylated group, right? It's the acid group with a methyl on the carbon, whereas the polymethyl methacrylate is the acid group is facing out and it's got a methyl stuck on the oxygen. And so that's the difference between those two. Yeah. And then polyvinyl chloride, you see the single chloride on there. So those are the real simple ones. A Kevlar has that aromatic ring and things, and it's got amide linkages. That amide linkage, again, that's how our proteins are, you know, so structured because of all the hydrogen bonding. And so that Kevlar has that kind of hydrogen bonding nature of our amino acids. It's funny that they haven't taken the amino acids and used them, because we can make amino acids, we can polymerize those. We don't have to do those in the body. It's funny that we haven't made synthetic polymers out of amino acids that were like functionally useful. You know, like you would imagine that with all of those building blocks that we know and that we can purify, that we would make commercial polymers out of the amino acids, just like we do with Kevlar. It's essentially an amino acid, but it's just not a biological amino acid. So maybe they tried it. I mean, it's a simple idea. Somebody's tried that, and maybe there's reasons. Maybe it's because our body would metabolize those things. But hey, you want to make a biodegradable plastic, make a plastic out of amino acids, and then it goes into nature and bacteria go, yay, munch, munch, you know. Yeah. The coolest thing I ever saw with amino acids was this Welch Welch Research Award winner at Scripps Institute. He swapped the chirality of these amino acids and did 4R and 4L amino acids, and they made ring structures so that the R groups stuck out like spokes on a wheel. And then these things would snap together because there were 4 carbonyls and 4 NHs, and they could snap together. And it would make these stiff tube-like structures that would disrupt the cell membrane and make it leak, and then it would kill the cell. And because they snap together, the cell would select its own poison. So you have all these rings out there that have all these different R groups, and one would get to the cell membrane protein and snap into place. And then another ring would come in and it's sort of sampling that cell's extra membrane protein, and the R group would associate with the protein, and then it would snap into place. It's really hard hydrogen bonding link, and it would just build this cylinder that would cause the membrane to leak, and it would kill that cell. And so he was finding bacteria and targeting specific types of bacteria with specific R groups on these cylinders. It's fantastic, beautiful work. Yeah. So there's future antibiotics that will work on some kinds of things like that. So that we worry about antibiotics. Oh, we're not doing any antibiotic research. You hear that in the news. It's not true. Yet again, the media lies. And that was like 15 years ago. So who knows how far they've gone. But that's an interesting polymer because it is snapping together. It's like a hydrogen bonding polymer, which is pretty cool, programmable. A lot of these questions seem straightforward. When it gets to like the bullets and the cartridges and everything like that. I've always wanted to, that's where I think I would enjoy a criminalistics course where we could go to the firing range and shoot and then analyze the rifling marks and stuff. Oh man, that would be great.
I always enjoyed watching Mythbusters when they would like they would shoot something or whatever with that gel, or they would like do something crazy. And
Yeah.
it was always like that, like that ballistics gel.
Yeah, I do. Yeah. I was watching some like home defense slugs. They make these slugs that expand and terrible, but yeah, in the ballistic gel, it's like, and everything. Yeah.
Especially that slow-mo like footage of it.
Yeah, I know. I wanted a slow-mo camera for just chemistry research years ago. $60,000. Yeah, you better get some subscribers if that's going to be your channel. So but some of those guys, like the slow-mo guys, it's the best. The guy jumped onto a trampoline filled with mouse traps with the slow-mo camera. It's great. Like he hits the trampoline and the mousetraps stay put, right? Like he goes in and they like goes underwater, but it's under the mousetraps, right? And then they all fall on him and they all snap. Anyway, that was the most weird one I've ever seen. There was another one that looked at silencers and it was a slow-mo of what's going on inside a silencer and how it slows down the gas and prevents a loud noise from coming out. And they made silencers out of plexiglass so you could video through the side. And they were looking at different baffle designs, the company that made them. And so they had the slow-mo guys come out and take pictures of it. And so they're videoing the silencer and the hot gases going in and out of the baffles and then leaking out. And that's all you got to do is slow the gas down. And then you don't have a loud report. It's like and on like the third shot, the plexiglass broke and splintered and just blasted apart. They got it on the slow-mo. It's so cool. You see the plexiglass just go, and start moving out. It's so good.
Will we provide it with some equations?
Yeah, I'm trying to think. Are there any calcs? Well, you definitely get that 3x3 matrix for the whatever it is, the ICC profile. Yeah, but there wasn't a lot of calculations in the physical section. Yeah, but yeah, you'll definitely. If I'm doing the test, like I'm doing the key or whatever, and I'm like, oh, I needed an equation, I'll make sure I put it on the equation sheet. Yeah. And then, like I said, if you finish this test and I get them graded, and then you're happy with your grade, then you don't have to take the final. So that's always fun. So everybody's like, all right, got to do good on this. Right. It's just a little graduation gift.
This final and advanced and organic final, they're on the same day.
Ah, dang, really?
There's also more.
Why would they do that? They're back to back on Tuesday, Thursday,
Yeah.
and then they know that you had those same classes. That's a dumb schedule.
Yeah, I think it's just like 15 minutes apart. Yeah.
Y'all need to write the registrar and tell them, no, nothing gets changed if students don't complain. And it's not like they're going to do anything to you. That's a legit concern. Say, look, we had Tuesday, Thursday classes, and our finals were on the same day. That's not cool. I know that I don't recall that ever happening before. So, you don't be a jerk, but say, this was, and that's, yeah, man, especially at this school, you guys are important to this school. They put a lot into, listening to the students and everything. And if you were to say, and, just email or you can email the chair, whatever, but say, this was kind of strange. Can you send this on to the registrar? That we had our Tuesday, Thursday finals on the same day. That's because that shouldn't have happened.
So how many questions do you
I would like to go ahead and pump it up to 50 so they're 2 points apiece.
multiple choice?
Yeah. But I mean, you got to burn through it. I mean, so there, again, there's not a lot of calculations. So it's not like you have to show a lot of your work. But if you do that, 3x3 and you show your work, you get partial credit unless you totally trash something. Yeah, exactly. So you have time to do it. Yeah, exactly. Yeah. Has it been a good semester?
Yeah.
Okay. It's a survey class, so it's, you go, what I say, a mile wide and an inch deep. It's like and so there's not much I can do about that. I did add a little extra depth to the explosives part because that's not in the book, but I had background in that, so I thought I'd go ahead and tighten that one up a little bit and go a little deeper. Plus, I think the people that have the forensic skills are also going to be useful in that sort of detect and disrupt and destroy type thing. If you know sort of all of the pieces of crime from studying after the fact, maybe you'll be important in preventing it, right? Do you know what to look for? And so that's my hope. Who knows? Maybe some of you guys will be on, anti-terrorism task force or whatever, and that'll be fun. Yeah. Yeah. What? Yeah, that'd be great. They have the same detectors and things like the Smith's detection for chemical warfare agents and stuff. They're in the subways. Somebody has to analyze the data from those and maintain them and decide what to buy, right? You're not going to put a GCMS in the subway because, it's too slow and all of that. But ion mobility spectrometer, yeah, it's real time, real fast. They have these biological things like air sampling for anthrax or things like that. And then it tries to do an ELISA test, kind of like the COVID test, real time, and then dump that. And, it breathes in air and bubbles it into a solution and then boop, 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 drops in there and does the little immunoassay and looks for these protein signatures, these antibody signatures. And, ping, we got an anthrax release in the subway, shut it down, stop the air handling, quit circulating it, so that's, the error rate on those is pretty high. So you got to somehow figure out if it's a real positive, not a false positive, but then you guys might be involved in making those things better because you have chemistry degrees. We didn't just give you a generic forensic science degree. We wanted this to be a chemistry degree because we wanted you to go into the labs and prepare you for that. Some schools have forensic chemistry, but it's really medical examiner assistant type thing. Now that's cool too, but it's not chemistry. And so we didn't want to give a misnomer and say it was a chemistry degree when it was really anatomy and physiology. So.
One last question.
Yes.
For like the super glue monomer, do you want us to know like the mechanism on how it polymerizes, like that it's an anion chain growth one?
No, I'm really not that interested in like whether it's cationic or anionic or free radical. More so that identifying the different monomers and things, because that's going to be the chemical signature that you're going to see in the IR or what have you. I thought in the book that was a little unusual because in most of the other chapters, the author didn't go into that much depth in terms of the chemistry, in terms of reactions and things. But in the polymer section, the author, Suzanne Bell, went into great detail on how every one of these is, every mechanism for every kind of chain growth. And I was like, wow, it's like a mini polymer course in here. But as far as detection, aside from the fact, the evidential value of maybe some of the initiators, like that nickel initiator, aside from that, I couldn't really see that where the evidence would be changed, whether it was cationic growth or anionic growth. It might change the number of head to tail, randomness you have or something like that. But I failed to see why it would matter whether it was cationic, anionic, or free radical.
Maybe it was her specialization.
It could be like mine in explosives. They're like, why did he go on explosives? It make it sound like Texas is full of clandestine bomb plants. And evidence suggests it's more meth and other pill mills. Right. So. All right. Well, then I wish y'all luck. Now, wait, stop. The person that's going to come up here and say, now I have 2 questions, I'm going to be really mad at. Okay, so go ahead and ask your questions now. Because that drives me crazy. Your question benefits others, and I know you're just shy and you don't want to ask the question. So if you got a question, ask it now. If you come up after everybody leaves, that's a pet peeve of mine. I'm just letting you know. So who is it? Anybody? Go ahead. All right, you were gonna do it. Okay.
I was just saying, I don't know if you had a question. I think it's more like, my head is, what else do I need to study? And what I'm looking at the weekly schedule. I'm like, oh, I just have to look at these slides.
Yeah.
I mean, that's my study thing, looking over these slides.
Look over the slides. Look at the homeworks. Make sure you understand all of these. Yeah.
Maybe top hat.
Yeah, but look at these and see, okay, that's sneaky DW. How's he going to change this problem? Is he going to make it backwards? What's he going to do? Is he going to put the answer as the question and then have the question be different answers, you know? And because that's what I'm doing. I was like, how can I change this problem? I can't just give them the same stinking questions. I know y'all were like, yes, you can. But a lot of times if I give the same question, I've had students miss it because the answers were, the program randomized the answers, right? And so they saw that question, it's like, oh, I remember that's B. They didn't even look at the answers, you know? And they go lesser and they're like, oh, it's so stupid. I just picked B because that's what it was on the homework. I was like, you didn't look at the answers. It's like, then you just missed that one for being silly. So, yeah. So does that help?
Yeah, I was
Okay.
just wondering, like, how else could I study for this? Like,
Yeah.
There's like an itemized list of things you should focus on.
focus on. Yeah, that would be nice.
This is it. Yeah. This is the list. Yeah. Yeah. The homeworks. All three of them. There's 3 on this section, right?
Yeah.
Oh, yes, the structures.
11 through 13.
11, 12, and 13. That's right. And the structures. Yeah. So looking at those structures. Okay. Great. Yeah. All right. Y'all have a great study time. We'll see you on Thursday. Oh wait. Thursday is our picture, our class picture. Okay. So don't come in your pajamas and wet hair, right? Normal test taking attire. Yeah. Okay, I'll do that. Yeah. Yeah.
Oh, wow.